Welcome to this presentation about the failure rate of QC-MDPC decoders. So this is a joint work between Nicolas Sendrier and myself. So in this presentation, I will explain why we want to have a low decoding failure rate and how we can achieve it. So we are interested in QC-MDPC codes in the context of BITE. So it is a code-based key encapsulation mechanism. And in the last specification, it is advised to use BITE2, which is the netherwriter variant of the scheme, rather than the BITE1, which is the McAleese variant of the scheme, in order to reduce the bandwidth by half. BITE uses quasi-cyclic codes, so it means that the parity check matrices that it uses are composed of two circulant blocks, and therefore they are fully described by only one row. So this is this achieves a reduction in the key size. It uses MDPC, moderate density parity check codes, which were first introduced by Misovsky, Tillich, Sendrier, and Barreto in the context of cryptography, and they show that there are reductions of the scheme to generate hard problems over quasi-cyclic codes. There have been some recent work on efficient implementation of the scheme concerning the encapsulation and decapsulation methods, as well as the key generation in the BITE2 context. The National Institute of Standards and Technology has shown interest in the scheme by choosing it as an alternate candidate for the post-quantum cryptography standardization process. So what is BITE2? What is the primitive behind it? So it's a netherwriter scheme. And so to generate a private key, you need to generate a QC-MDPC code. So you generate a sparse matrix that is composed of two circulant blocks. So here the two blocks have size R by R. And they have a raw weight for each block, which is W/2. So here the weight has to be about the square root. W has to be about the square root of the length of the code, so the square root of 2R. Then to generate the public key associated with the private key, you put the matrix in systematic form by simply inverting the first block. So then, when you have a message, which is a vector E0, E1, that has a length n and has a weight t, so here t is the square root of n as well. So to encrypt this message, you compute the syndrome that it gives with the public key. And then to decrypt, so to recover the error vector, you need to decode. So for this, you use the sparse parity check matrix, which is the private key. And if you have a sparse parity check matrix, you have an efficient algorithm, and we will discuss this point later on. But if you don't have a sparse parity check matrix, you cannot decode easily. The problems become hard. So here in this slide, I've written the scheme using the cyclic polynomial ring point of view rather than the matrix, circulant matrix ring point of view, but these two representations are isomorphic. And I've given a few examples of parameters. So for lambda bits of security, I give the value for WT and the block size that you should use to have in CPA security. So the scheme is based on two hard problems on quasi-cyclic codes, which are the quasi-cyclic syndrome decoding problem and the quasi-cyclic code word finding problem. So the first one relates to the security of the message, and the second one relates to the security of the key. So the best known algorithms to solve these problems are variants of the Prange algorithm, which is an information set decoding algorithm, and it was shown by Canto, Torres, and Sendrier that all the improvements of this algorithm have the same complexity asymptotically. So it is for the first one about in 2 to the t, and for the second one it's in 2 to the w. Then since it's the quasi-cyclic variance of the problem, you have to consider the fact that you can use a multi-target variant of the information set decoding algorithms, and this way you gain a factor about the square root of r for the first problem and the r and of r itself for the second one. So now, why do we have to pay attention to the decoding failure rate for BIK? It's because it uses Fujisaki-Okamoto transformation to make it to provide in-CCA security. And if you look at the analysis by Hofheinz, Hoffelmans, and Kiltz of this transformation, they show that you need to have an encryption scheme that is delta correct, and delta should be less than 2 to the minus lambda. So if we break down the expression of the delta correctness, we see that in the middle we have an encryption of a message with the public key that then we decrypt with the private key, and we want to calculate the probability of the input of this process being different from the output. So here there is also a maximum over all the possible messages, but it's we can remove it when we talk about BIK, because in the encryption method there is already a randomization process. So in fact what we have between the brackets is just the DFR for a specific private key and public key. And in the end, we are interested in the expected value of these probabilities for all the possible keys. And in fact, what we have is just a DFR of the scheme for a given decoder. So if we summarize the requirements on the security when we use a Fujisaki-Okamoto conversion, so first, to have in CPA security, you need to make sure that the underlying problems offer lambda bits of security. And to have in CCA security, you need to pay attention to the DFR, and it needs to be less than 2 to the minus lambda. So the first two items depend marginally on R, and they depend mainly on T and W, and the last one depends mainly on R. So this gives us a methodology to find parameters for BIK. So first we will choose W and T so that we have in CPA security, and we will fix those values and then take the relevant block size R that also depends on the decoder that we use. And in fact, in practice, if the third condition is not verified, it was showed by Guo, Johansson, and Stankowski that there is a practical attack on the CCA security of the scheme. So what can we say about the DFR of a QC-MDPC decoder? In a previous work, we designed a simple sequential bit flipping algorithm, and we showed that it can be modeled using a Markov chain. With this model, you can calculate probability of failure. So you can predict for a given set of parameters W, T, and R the DFR for this decoder. So we applied the methodology that I just explained. So we fixed W and T so that we have in CPA security for some level of security lambda, and we took block sizes in a range values, in a wide range of values. And for each one of these values, we computed predicted DFR. We did the same thing for simulation. So we simulated the algorithm and counted the number of failures that we obtained. And the difference with this is that the range of values for R that we can use is narrower, because when R is too big, it's really hard to measure any failure. So we have experimental data only on a smaller range. And what we observe is that the behavior of the two curves were really similar In fact, the two curves only had a small difference between them. This gives us confidence in the fact that the model is a good model. And so we can use it to see the general behavior of the DFR for the QC-MDPC decoder. And what we observe is that the function, the logarithm of the DFR as a function of R, is always a concave function. In fact, the worst case is for really high values of R, and in this case, it's an affine function. But this concave behavior was already observed with all the algorithms that we tried for decoding QC-MDPC code. I should mention the asymptotic result of Jean-Pierre Tillich. In this work, he showed that the DFR is upper bounded by an expression, and if we look at this expression, we can see that it's a concave function of R. Here it's in a slightly different context because W and T grow as the square root of the code length, and they are not fixed. But I think it's interesting to mention anyway. So this knowledge of the DFR led us to formulate a new security assumption. So this security assumption depends on the decoder, and it also depends on a security level. So it means that W and T are fixed. So what the assumption says is that the logarithm of the DFR is concave. So we will use this assumption to estimate the DFR of an efficient algorithm, such as the one that I will explain in a few slides. So the way we use it is as explained in the illustration. So in the illustration, you have the blue curve that represents the typical logarithm of the DFR, and the black dots are what we can actually measure. So we can measure this with a simulation by running many simulations so that we have precise points. And what the assumption implies is that the any tangent of this curve, on the blue curve, is always above the curve. So if we use the points that we know, the black points, so we take two close points, we can draw the tangent and use this tangent to estimate. For example, for the block size R, we know if the assumption is true that the DFR is below 2 to the minus s. If we take the converse point of view, if we want block size such that the DFR is less than 2 to the minus lambda, we can take, for example, here RD lambda. So there is a condition that I didn't mention in this assumption, is that we limit the range of values for R on which it holds. The reason for this is that the blue curve can have an inflection point. So after this inflection point, the slope will not be as steep as before the inflection point. So this means that the concave assumption is not true anymore. But this phenomenon is known for LDPC codes, and we have it for MDPC codes as well. But one origin of this phenomenon is the low-weight code words. So by construction, in an MDPC code, you have many low-weight code words, and if the error pattern, so the message that you encrypt, is in some specific configuration regarding to these code words, it can lead to a decoding failure. But the probability of being in such a configuration is really small. For the byte parameters, for example, here for 128 bits of security parameters, it's about 2 to the minus 400s. And we have some further ongoing work on the error floors and the wikis, and so far we couldn't find anything that invalidates the assumption. Now we can discuss the decoding algorithms for QC-MDPC codes. So here I will describe the bit flipping algorithm, and then we will see a modification that improves the decoding performance. So the inputs of the algorithm are the sparse parity check matrix H and the syndrome S. And the output will be with high probability the error vector E that gave this syndrome. So the important part of the algorithm is the part in red. It is the part where it makes decisions. So these decisions are made for each position based on their counter. So the counter is the number of unverified equations involving this position. So the intuition is that for an error, this value will be high, and for correct position, this value will be low. So to try to reduce the number of errors of the pattern that we are decoding, the algorithm will flip all the positions that have a counter that is too high, that is above some threshold. And then it will, after doing many flips, it will recompute the syndrome and restart the same process until it has found all the errors. So it will know that it has found all the errors when the syndrome is 0. So the problem with this algorithm is that sometimes it takes bad decisions. So bad decisions happen when a correct position has a high counter, because the risk is that the algorithm will flip it, and by flipping a correct position, it adds an error to the pattern, and this error will be harder to detect. And if we make too many of these bad decisions, the progress of the algorithm will be hindered, and it can even lock the algorithm. So we want to introduce some ideas from soft decision decoders. So these decoders have better decoding performance, but they are more complex. So what we want to do is to keep the simplicity of a bit flipping algorithm and to add some ideas from soft decision decoders. So we will do this by using the reliability information that we obtain with the counters. So when a counter is really high, we have more confidence that it corresponds to an error. So it means that when we flip it, we have a lot of confidence in this flip. So what we will do is that we will use this confidence information to limit the duration of a flip. So each flip will have a time to live that will be computed when it's flipped, when it's active. And at the end of this duration, the flip will simply be reverted. So of course, the higher counter, the ones for which we have more confidence, should be kept for a longer time than the ones that are just above the threshold. So here I give the description of the backflip algorithm. So to highlight the fact that it's just a bit flipping algorithm with something more, I've put in red the differences between the bit flipping and the backflip algorithm. And so the first part is the part that handles reverting the obsolete flips, and the other part is the one computing the time to live, so TTL. It's a function of the difference between the counter and the threshold. And so this part also stores the information about the TTL. So how do we choose this time to live function? So as I said, it's a function of the difference between the counter and the threshold, and we want it to be an increasing function because a high counter should be kept for a longer time than a small counter. So the empirical choices that we made for this paper are to take a saturating fine function, and we found the parameters of this function by using an optimization method on the DFR. The results of this optimization are given in the table. For the thresholds, we will use the theoretical results of Julia Chollet in PhD thesis, and the threshold rules that were derived from the theoretical model. I won't go into the details of the expression, but what we can see is that it depends on the syndrome weight S that we know all the time, and the error weight that we don't know all the time. So we could try to guess it, but actually with the backflip algorithm, an interesting strategy is to take t minus the number of flips that we have done so far. So this way, if the algorithm has taken only good decisions, the value will be exact. It will exactly be the number of errors, and so the threshold will be optimal. But if it's not, so if the algorithm has taken some bad decisions at the beginning, then this will give some more conservative threshold, and this way in the iterations after some bad decisions, the decisions that are taken will be safer. And on the other hand, after a few iterations, the bad decisions of the beginning of the decoding process will be reverted, and this way we have won on two fronts. So to show the performance of this algorithm, we compare it in this figure with two other decoding algorithms. So the first one is the original bit flipping algorithm, and the other one is the one-round decoding algorithm from earlier versions of BITE. And we can see that between each algorithm there is an order of magnitude of improvement. And finally, we can use the extrapolation method that we've explained to find parameters that we could use with a backflip algorithm in different configurations. So for example, if we limit the number of iterations to 110 or 11, and for the different lambda security parameters, we put in this table the values that were used for the extrapolation method, and then the values that gives the block size that gives a DFR that is at most 2 to the minus lambda with the decoding assumption. And we can see that compared to the CPA parameter, in CPA parameter, the increase is between 15 and 36%. So in the end, we have explained the status of the DFR in the security analysis. We have justified and formulated a new security assumption that relates to the decoder. We have explained the rationale of the backflip decoder, and we have shown that it shows good performance, and if we were to use it in a bike scheme, it will use small blocks